Alright, let's talk about chemical bonding. Namely, in this first video here, we're going to talk about Lewis structures, and later on we'll get to VSEPR. If you remember from the last chapter, we ended talking about valence electrons in that chapter. It's one of the last topics that we covered. If you remember, valence electrons are the electrons that are the farthest away from the nucleus. They have the largest, or the highest principal quantum number. So it would be the 2 here. 1 is lower than 2, obviously, and so that is not valence. Everything that has the highest occupied principal number is going to be valence. So this particular element, oxygen, has 6 valence electrons because it has 6 electrons in the highest occupied principal shell. Like I mentioned, these are the farthest away from the nucleus, which means that these are the only electrons that can interact with other stuff. They're the only electrons that can actually participate in chemical reactions. And so when we are writing and representing molecules and how the electrons and molecules bond different atoms together, what we're really concerned with are these valence electrons. And so we're going to kind of make a shortcut here. When we start to represent molecules, we don't have to represent all of the electrons in a molecule. We really only have to represent the valence electrons, because again, those are the only ones that are doing stuff. It's important that the rest of the electrons are there, but they're not really participating in anything. And so the way we're going to do this, or one of the ways that we can do this, and it's by far the most common way to represent electrons in undergraduate chemistry classes, is doing what we call Lewis structures. And so what a Lewis structure or a Lewis dot structure does is you take the symbol for the element that you have in a molecule, and you have a dot for each of its valence electrons. So one dot for each valence electron. If you remember from the previous slide here, oxygen had 6. And so here in our Lewis dot structure, the oxygen has 6 dots. We're going to pretend like each of our elements here is a 4-sided box, and we're going to distribute those dots evenly around the box. So we're going to start by putting just 1 on each side, and then if we have more than 4, we'll start to pair them up on each side. We don't actually care if when we start pairing them up, if they're on the sides right next to each other. That doesn't really matter. Just as long as you don't pair the dots up first of all, you only pair them up when you have to. So we have 8 possible spots for electrons around here, and there's a good reason for that, because that is the highest number of valence electrons that we are going to see in any of these elements. If we have 8 valence electrons for an element, that is what we call an octet. If something has 8 valence electrons, that is an octet, and that is extremely stable. Everything wants to have that octet of electrons. So neon here, in our example, this is our example of a noble gas. Neon has 8 valence electrons, and it is very, very stable. Fluorine is 1 away from getting that octet, and so fluorine will do pretty much anything to get that 1 electron. It will steal electrons, it will share electrons if it has to, it will do anything that it can to get that octet. And most things are kind of similar to that. Fluorine is kind of an extreme example, but other things will do whatever they can to get an octet of electrons. And so here we see the Lewis dot structures for the elements from lithium through neon. So lithium is element number 3, neon is element number 10. Lithium has 1 valence electron, and so it gets 1 dot. Beryllium, which is right next to it, has 2 valence electrons. It gets 2 dots. Boron has 3, carbon 4. Once we get up to 4, if we're going to put any more in there, we now have to start pairing them up. And so the nitrogen, which has 5 valence electrons on one side, it doesn't actually matter which side, It could be up or down or left or right, doesn't actually matter. Just on one side you'll have 2, and then you'll have 3 unpaired electrons on the other 3 sides. Again here, with oxygen with 6, 2 of the sides are going to have 2. It doesn't actually matter which 2 sides. They could be next to each other, they can be opposite, it doesn't matter. But we're going to have 2 sides that are paired and then 2 sides that are unpaired. And then we'll have fluorine right here with 7 valence electrons where only 1 is unpaired. So when we have these atoms with their Lewis dot structures and they're trying to make molecules, they do this by either trading or stealing electrons to get an octet. So they can either transfer electrons or they can share electrons to try to reach this octet of electrons in the molecule or for that particular atom. And this is bonding. This is how and why things bond together, is they're trying to get to that ideal state, the lowest possible energy, which for most things is having an octet, and for our purposes, all things. As with all things in science, there's exceptions to everything, but we are not going to worry about the exceptions. We are going to worry about the rule here, which is that everything wants to have an octet. So, if something is going to steal to get an octet, this is what we call ionic bonding. So ionic bonding, if you remember from earlier in the class, this is when we have a metal and a nonmetal. This is always going to be the case here. If you're going to have ionic bonding, you're going to have a metal and a nonmetal. You're not going to have ionic bonding between 2 nonmetals, or even 2 metals for that case. It is always a metal and a nonmetal together. And the way that's going to work out, so here for example with potassium chloride, the potassium has 1 valence electron, the chlorine has 7. The potassium is going to give its electron to the chlorine. Or if you want to think of it a different way, the chlorine is going to take it. The chlorine is going to steal that electron. And so what you end up with is the chlorine with its full octet, and the potassium looks like it doesn't have any valence electrons. But in reality, once you remove that single valence electron, what you have underneath is what we call a discovered octet. And so the potassium actually does have an octet as well. It's just because we removed the single electron in the, let's see, what would that be? Potassium, that would be the 4s. So potassium has 1 electron in the 4s. When that electron is gone, all of a sudden it now has a new octet in the 3rd level. So it will have 2 electrons in the 3s and 6 electrons in the 3p. And if you don't believe me, you can go back and write out the electron configuration for potassium and see what you're left with when you take that 1 high energy electron away. And so both of these now have an octet, and they are both happy. When we're actually writing the Lewis structure for ionic compounds like this, just by convention, as far as I'm aware, there's not really a good reason for why we do this other than just everyone agrees to do it. We put the anion in these square brackets, and we just leave the cation without its electrons showing. So again, it does actually have an octet, but we just leave it blank, and it's understood that it has an octet. So with that in mind, why don't you pause the video here in just a second, and try to draw the Lewis dot structure. It'll look relatively similar to this for magnesium oxide. So go ahead and pause the video now and try to do that yourself. Alright, I hope you paused it and attempted this on your own. We're told we have magnesium and oxygen. If we write out the Lewis dot structure for each of those elements individually, what we'll see is that magnesium has 2 valence electrons. Sorry about that. This pad here is a little bit troublesome sometimes. So magnesium has 2 valence electrons, and there's a couple different ways we can figure that out. the easy way is just to look at which column in the periodic table it's on. The hard way is to actually write out the entire configuration. Not that it's all that much, not that it's all that difficult with magnesium, but I don't think I actually talked about this in the classroom, but magnesium is in the second column on the periodic table, which means that it has 2 valence electrons. Everything in the second column has 2 valence electrons. Everything in the first column, so column 1 or 1A, depending on which numbering system you're using, everything in that column has 1 valence electron. We're going to skip over the transition metals for now, although the transition metals, just so you're aware, all of them have 2 valence electrons. But when we get to column 13, 14, 15, 16, 17, and 18, they just follow that second number. So everything in column 13 has 3 valence electrons. Everything in column 14, that's the carbons column, has 4 valence electrons. Nitrogen column is 5, oxygen column is 6, fluorine column is 7, and then the noble gases are 8. So anything in the column with oxygen has 6, anything in the column of fluorine has 7, and that's the easy way to work out how many valence electrons something has. So oxygen is in column 16, it has 6 valence electrons. So we have 1, 2, 3, 4, 5, 6. And actually I kind of cheated there a little bit because I knew it was going to work out this way. Technically I should have put 1, 2, 3, 4, 5, 6, but just habits, I knew it was going to work out this way, and so I just did it the short way. So this is what we start with. We're trying to get everything to have an octet, and so what's going to happen here is the magnesium is going to give up both of its electrons to the oxygen. You don't have to draw the arrows when you're doing this, by the way. It's just I'm doing that to try to make it more clear what's going on. And so what we're left with is magnesium 2+, and then again, just by convention, we'll put oxygen with its full octet in square brackets. All right. Hopefully that makes sense. In the next video here, we're going to talk about the other way that things can bond together, and that is covalent bonding. So I will see you in the next video.